All right. Welcome. So I just made Twitch affiliate, whatever that means. I still haven't figured it out.
Congrats.
So I'll sort that out as we go. I figured out that the level between Twitch affiliate and Twitch partner is like
It's massive, yeah.
way up there. But I mean, that's not why I'm doing it. It's just like, oh, Twitch affiliate.
Yeah.
What does that mean? Anyway. All right, let me pull up the agenda here. And I'm going to send this to all of you so you can just follow along as we go. So I'll put it into chat. If I can learn how to actually copy things into chat, let's see if I can. Oh, it doesn't want to paste it. That's really interesting. Yeah, it didn't save all of it. So location in just a moment. We end off with temporary storage areas. Yeah, I'm not going to do it that way. I am going to send you an actual document via chat. You'll have access to this whole thing afterwards, but I want you to have it so you can follow along with what we're doing today. So let me see if I can figure out how to download this. There we go. Export to PDF. Oh, good. Who just arrived?
For small files, you can also post them to Discord, but their message limit is pretty, or their size limit is pretty restrictive.
All right, so here we go. And I'm going to put this in downloads. And I will now send it to you. All right. All right, tell me if that PDF arrived in chat.
Yes, it did.
Excellent. Okay, good. All right, so for anybody who's viewing this either live or at a later date, what you're looking at is the 5 Live Free Code School. Here are our 5 students. I'm Eric Rose, I'm the instructor. This is an education in how to be a well-rounded entry-level full-stack developer. We're at our 3rd session, and today we're going to cover binary and how the CPU works in detail. We covered some of the fundamentals of the CPU in our last session. All of the resources and such will be available. You can look at Twitch and find all of my socials and just follow along to my blog or my YouTube channel, and you'll find everything there, including the homework as well. I've got homework assignments that we'll do. This lesson that we're going to go over is really, I wrote it as if we had 2 days because we're going to do tonight and tomorrow night. We're going to get as far as we get today, and then we'll pick up again tomorrow, but it's about 2 nights worth of material, including homework. So when I put it up on the different platforms, I'll break it apart, but I've got everything in front of me. You're going to see that in the PDF. I want to start though by having introductions. We all did that a couple sessions ago, but Jonas wasn't able to make it. So Jonas, I'd like you to introduce yourself to everybody. You can see in the PDF what we're looking for, who you are, anything about your bio, where you live, anything else you want to share, what prior experience you have in tech, and particularly what your goals and dreams are as far as technology. And you have to end off with an interesting fact about yourself. So if you can follow along there in the PDF and just tell everybody in the class about you.
Okay.
Do you see that at the beginning of the PDF? I give you your own section. Introduce Jonas Wildemichael or Weldemichael. Am I saying it right?
Yeah, it's right.
Okay, good. I can just call it out. So just tell us about where you live and anything else you want to share.
Okay. My name is Jonas Wildemichael. I'm from Addis Ababa, Ethiopia. My story is a bit kind of weird, I joined university at the age of 32.
That's well done.
Yeah, I studied for about 4.5 years. the undergraduate program is for 4 years, but because of the pandemic, our university was closed for about 8 months. So it took me 4 and 6 months. So now I'm 36 years old. It took me persistence.
Yeah.
It's a little bit hard when you're a bit old and just join university with teenagers. It's a little bit difficult,
I'll bet. And you were telling me that the education system there, even though you got a 4-year degree, it wasn't that hot, right? Wasn't that good?
It wasn't good, First of all, it's not project-based learning, Computer science is this software development is a technical field.
Yeah.
You don't learn it by reading books or by attending theoretical lectures.
Right.
You have to build stuffs,
Yeah. We're gonna build a lot of stuffs.
Yeah, but that wasn't the case here. Just we focused on the grades, just on fulfilling the class requirements.
Yeah. Okay.
So,
well, you told me a bit about this before, but I want to hear it again. Like, what are your goals in terms of technology and work?
My goal is to become a software developer, specifically web developer.
Okay.
To become full stack.
Yeah.
My tool of preference is JavaScript. Just to acquaint myself with technology. You have to pick one language at first, and that's my choice. And I'm glad this School of Ours 5 Live School chose JavaScript as a tool of learning.
Yeah, I almost chose C# because that's what I did for like 15 years, and I was late to the party on JavaScript. So we almost went C#, but JavaScript is really, really cool now. It's really cool. 10 years ago, I would have been like, no, stay away. I want nothing to do with JavaScript, right? But it's pretty cool. Anyway, keep going.
So that's my
that's your goal.
My goal, yeah.
And an interesting fact about yourself. No pressure. Whatever you want to share.
Okay. I'm an introvert.
Okay. Okay, good. Well, it's a small class of 5 people. You're going to get to know us all really, really well, and vice versa. Yeah, there might be people watching, and there will be after the fact, right? On these recordings. But this is what I stressed. I know you watched all the recordings, right?
All of them, yes.
Yeah, I just want to tell you, I want to tell you right now live, this class really is for the 5 people that are in here right now, right? You're my primary students, and you're going to get my focus. And you should feel safe here. Like, it's okay to ask questions. It's okay to not know the answer if you get asked a question. It's okay to say, hey, Eric, I don't know what you just said. I didn't follow that at all. Like, in fact, I want to hear that. I'm not bothered by that. In fact, I welcome it because 1, I get a chance to correct it immediately. And 2, it just makes me a better teacher over the long haul. So, and again, to remind all of you, anytime you want, break in and just ask. Okay?
Okay, that's great.
Good, awesome. All right, now the next thing is I wanted to review homework and projects. I'm going to have detailed written feedback. The obligation that kept me pretty, busier than all heck yesterday stopped me from getting all that done with the prep I had to do. But I do want to say this: there's a particular thing that I saw every single one of you do that I really, really appreciated. None of the essays you turned in included any sort of like highly technical terminology or anything that would make a novice to the field just sort of glaze over. You really did seem to take to heart, hey, listen, what if you were going to explain this concept of you know, what a computer is and how it works to a novice, to a bright teenager. And you did an exceptionally good job of that. The one thing really that I was looking for is someone going to overcomplicate this? Because that's a common mistake we make as technologists. By the way, I just want to give you a little bit of hope for the future. Sometime about, you know, a month or 2 or 3 down the line, there'll be a moment where you suddenly step back and just start to take stock of everything you've learned. And it's going to be a lot. We won't even be done yet. And this will probably happen. And you start to realize, man, I've learned a lot of stuff. And we're going to do it at the right gradient. So, you know, you'll understand it all, but there's going to be a lot of stuff. And by the time you're a working developer for a year or two, it can be very easy to forget where you were and how little of these fundamentals about programming computers and such the average person knows. And so I just wanted to have you write it that way, to just never forget that your ability to take these complex concepts and make them simple and well understood isn't just something for me to see how well you understand it. It's not an academic thing. It's one of the key things I've seen successful developers do, especially not in the quality of the code they work or they write, but in their personal interaction, how well they work on a team, how well they work with non-technical folks. It's a really key thing. And every single one of you did a really good job on that. Jonas, I would like to see you take a stab at the same thing. Okay. If you need help after the class, I'll show you the exact homework thing, but it's really just explain what a computer is and how it works as if you were talking to a 12-year-old. Okay.
So do that.
Okay, good. All right. Next thing I want to do is just see if there's any questions that have come up during this week that you're like, oh, I can't wait till we're in class. I want to ask Eric about this or that. Is there anything that someone has top of mind they want to ask about before we get into the material? Okay, cool. All right. So we're going to get into binary. Now, quick question. For those of you who are reading through the book, You Are Not Stupid, how many of you have gotten through or past the point where we explain binary? Okay, good. Jonas, have you read through that far?
No, I haven't got the copy yet.
Really?
Yeah.
Let me get you a digital one. I'll get you after class tonight. I'll get you a digital copy that you can read on your computer. Okay. I'll take care of however we need to do it. If I need to get you a Kindle copy or whatever we need, a PDF, I'll get you a copy. Okay.
Okay. Thank you.
So as we go through this, I'm going to be asking a lot. It isn't just going to be me lecturing at you. I'm going to ask your thoughts, your opinions on these things. So expect it to be kind of interactive, but we'll get all the way through binary. And we'll even talk about a couple instances why it still matters. As a programmer, we all use these modern languages like JavaScript and C# and Python and all of these. And there can be this idea that binary doesn't matter anymore, but there are definitely instances where binary still does matter and it helps. But let's just get started. The first thing I want to ask is just if someone can explain in simple terms what a number system is. Any thoughts, any ideas on it? What a number system would be?
Would it be like, because I remember reading about like the base, like binary is base 2. So it's kind of like the way of which we count, like how many numbers we count up to maybe, or? Yeah,
you're totally on the right track. What she's talking about there specifically is that there's a certain way of building a number system that uses a term called the base. And we'll get to that in a moment. But I want to step a little teeny bit higher than that even, and just put out the idea that a number system is something that civilizations around the planet have had for a long time. And it's just simply a way to use symbols to represent quantities. And that's it. How do we use symbols to represent quantities, right? One of the number systems that most people, at least in the Western world, are familiar with, if only from popular culture, is Roman numerals, right? We see them all the time in sporting events and that sort of thing. It's a number system. Can anybody tell me some of the common symbols in that Roman numeral system?
Well, it looks like an I for like a 1.
Yeah, it's funny. I always call it an I too. And the funny thing is I took Latin when I was like 14. There's probably another term for it. Don't know, don't care, but it looks like an I, right? What's another symbol that's used?
It's a V.
X.
An X, absolutely, Jonas. And there's a V. There's a couple others that we see all the time. 3 others.
L.
N or M?
L, like
L,
Lola.
absolutely. L. Yeah. We see L in there.
C.
C and M. Does anybody know the quantity each of those represents?
Maybe. It's far away. I think
Yeah, that's
L
fine.
is C is 100, L is 50,
Yeah.
V is 5, M is 1000.
Yeah.
Yeah.
You got them all. Good job, Ellen. That's exactly it. And the funny thing is, I mean, I forget some of them too, but then it was when we're in America, right? So when we hit Super Bowl 50 and they had the big L on the screen, like, oh yeah, that's right. Roman numeral L, that stands for 50. It doesn't work the way our number system decimal works. There's an odd sort of logic to whether, you have, you've got these I's and you put the V before or after and before or after the X. There's some logic there. We're not even going to get into it. I just want to point out that the rules on that are kind of odd, and you either have to kind of figure them out or read about them, and we hardly ever use them. But they're different than what we use. What we use is a number system that's common all over the planet, and it does use a thing called a base. So let's step back to the big picture, though. We're using symbols to represent amounts. And key to figuring out number systems like binary and hexadecimal, which is another one we're going to look at, is understanding that when you're studying them, you're going to be looking at symbols that you're not going to think of as symbols. You're going to see, for example, the number 1 or the number 2, for example, and you're going to think that that represents the quantity of 1 or 2. And even worse, you're going to see a 1, for example, followed by a 0. And you're going to think that that represents a quantity of 10. And the key that I've found to like stepping back and sorting this all out is looking at that little thing that looks like a 1 and recognizing it's just a symbol. We could use any symbol there. We could use a smiley face. We could use an emoticon. We just need a symbol that represents a specific quantity. So as we start, I'm going to sketch here in a moment. We're going to look at some examples, but that's the first thing to separate out in your mind is we're going to look at symbols. So let's see if we can do this, this sharing thing. I'm going to get hopefully better and better at sharing my screen and all that kind of stuff. Okay. A Power. We got this app called A Power Mirror. It doesn't flow off the tongue very smoothly and easily. All right, it's taking a minute to start up. How many of you studied binary in some sort of class before?
We took it in the freshman introduction to computer science course.
Okay, good. So it's been about 5 years.
Yeah, about binary decimals, about hexadecimals.
Yeah, good.
Yeah.
And
binary is the basic numbering system when we are understanding about how computers work.
Yeah,
in the CPU.
right, exactly.
It's all about ones and zeros.
That's exactly where we're heading. You're totally right. And then Jason, where did you learn about it?
I'm not probably when I took my A+ in like 2004, I guess.
Okay. Okay.
That's probably the first time. I don't think I studied it like formally in a class or anything, but it was probably around that time, I'd say.
Okay. For some reason, A Power Mirror isn't starting up, which is wonderful. So you have to give me a minute until I figure out why it is being a pain. I have another way into this. All right, let's do this. I'm going to cheat by opening up, by bringing my iPad into the meeting. All right. Okay. I think this worked. Okay. Let's get some Zoom controls out of the way. All right. And if anything doesn't work out here in terms of the image, what you're seeing, let me know. Okay. So first, I want to talk about this concept of a base. Oh, I remember, this is not the app I want to use. I found a different one that worked a lot better. Give me just a moment. There it is. It's what I was using last week. Okay, Nebo. All right, so 5 live, add new freeform. Okay, good. So let's talk about this concept of a base. Can anyone explain what this term means? For a number system?
The base is, the number of digits that we use in the numbering system. For example, in a binary, we use 1 and 0, so its base is 2. In decimals, we use from 0 to 9, about 10 digits. That's why it's called decimal. In hexadecimal, we use the 10 digits and letters from A up to F.
Good. All right. So let's examine this for a moment. Okay. You are 99% correct. And the 1% honestly doesn't matter, but just hear me out on something. I like to think of this as, you're right, a base is a number. It's 2, or it's 10, or it's 16, or others. But it isn't really technically the number of digits. It's actually the number of symbols. And the only reason I point that out is because when we look down here at the hexadecimal system, we all think of 0 to 9 as digits. But this, an A, a B, a C, you can call them digits, but I really like giving it a proper name of, well, it's a symbol. A symbol is something that represents another thing. That's all. And yeah, the 0 through 9, they kind of represent other things as well. But here it becomes very concrete. None of us think of A as representing a quantity or an amount of things. You don't say, I have A apples in my bag at the shopping, my shopping cart. You'll sound really weird. So I just find it helps to remember that all this is actually a symbol. And we'll look at hexadecimal in a moment here, okay? But you're spot on, Jonas, that the base for a number system is how many symbols or how many digits do we use? Any questions so far?
Okay, I can clarify a little bit. For example, in hexadecimal, one digit is expressed in 16 ones and zeros. In decimal, one digit one digit is expressed in 10 ones and zeros. In binary, it's in, okay, I'm lost, sorry.
That's fine, no problem. We'll get to it. I want to start with the one we're all used to, just so we understand the terms. So we already have one term, or the terminology. First one is we have a base. And what is that again? What's the definition of base?
Symbols
Or
to
symbols.
represent quantities.
Number
oh, yeah, number of
of.
symbols. Yeah.
Exactly, number of symbols. Good. The second thing we're going to look at is called a place. Can someone take a crack at describing what place means in a number system?
How many symbols total we're gonna get?
No, this is still how many symbols total. That's base. Here we'd have 2 symbols for binary, or 10 symbols for decimal, or 16 symbols. Place is another thing.
It's the position of the number.
It's a position of the symbols. The second thing is position tells us the order. Now, I want to explain what I mean by order. Order is a word in English that has several meanings. This one means relative magnitude. One can think of a little teeny hill, and one can think of a giant peak. The order of magnitude is vastly different. That's the definition we're kind of thinking of here with order. We're not thinking of, 1, 2, 3, 4, or a line waiting for to go into a big event where I'm first in line, you're second, someone else is third, a fourth person is in fourth. That's not the order we're looking at, okay? We're looking at here, what's the relative magnitude from one position to the next?
Is it place as place value in math?
Yes, that's another
Okay.
term for it, is place value. Let's see if I could actually do that in some nice typing. Place value. This is exactly the same term, okay? And again, this is something we're all totally used to in decimal. So I want to explore decimal. We're going to write out 3 places. Now, we're going back to 2nd or 3rd grade. I want to acknowledge that. But I want to do it in decimal, the system we're always used to, so that when we make the transition to other number systems, the terminology comes through very easily. So this is a place. We'll call it place 1. This is a place 2, and this is a place 3. And right in here goes one of our available symbols. A symbol goes here. A symbol goes here. A symbol goes here, and so on, and so on. At least in the number systems common in the Western countries, we start at the right and we go to the left. There are other number systems, but they don't relate to what we're learning in computer technology. So there's actually a formula at work here. And to understand it, I'm going to give these places their actual proper numbers. Watch this. It's been a long time. If I get this wrong, I'll just correct myself. Okay. So we had this idea that the place is a magnitude. More precisely, it's the relative magnitude. Well, related to what? Well, related to 2 things. How far we're moving to the left. So Here's the factors. 1, move left, and 2, base. You sure what I mean? Let's reconstruct that same thing. We have place 0, place 1, and place 2. The symbol here, whatever it's going to be, is used to indicate how many we have of the base raised to the power 0. Here, it's how many of the base we have raised to the power of 1. And here, it's how many of the base we have raised to the power of 2, and so on. So if our base is 10, we have 10 to the 0. We have 10 to the 1. We have 10 to the 2, and so on. This means, and by the way, I'm not going to get into the math behind this. I am not a math nerd. Anything to the 0 power is 1. Anything to the first power is itself, so it stays 10. This is just 10 times 10 is 100. So we all know from doing our basic elementary school, this is the ones place. This is the tens place. Put a little S there. This is the hundreds place. But I want to show you that it's not something you just need to memorize. We all did in school. We all know that this is the ones place, this is the tens place, that's the hundreds place. But the specific reason why is that the way math nerds designed the number systems used in the West, they say, let's start with the base and the relative magnitude as we move left is related to powers of the base. This is base raised to the 0 power. This is base raised to the 1 power. This is base raised to the 2 power. And again, I know we're going back to elementary and middle school math, but you need to know this cold in order to translate it over to binary. Any questions so far? Okay, so now we get to the question mark. We said there were question marks in here. This is where the symbols can go. What is in decimal? What are the available symbols we can put in those boxes?
0 up to 9.
0 to 9. So if there's a put a different letter here. If there's a 4 here and a 2 here and a 5 there, the actual math is the symbol, we use SYM, times place raised to, sorry, not place. Yeah, it's base raised to the place. That's the formula. So here in the first one, we have 4 times the base, which is 10, because it's decimal, raised to the place, which is 0. That's how we figure out the quantity. That equals the quantity. Now, again, we've all done this. We can do this stuff in our head super fast. We know that that's 4 and that this is 20 and this is 500. We know this, but I want to show you why, because this formula, Q for quantity, this is what will unlock binary and hexadecimal and any other weird number system you come across. Any questions so far? Well, then let's do the math on the next ones. What is the math on this one right here? Someone tell me the numbers to write down.
2 times 10,
2.
raise it to 1.
The base is 10, raised to the 1 because that's the position. 10 to the 1 is 1, so 2 times 1. Oh, sorry, 10 to the 1 is 10, so 2 times 10 is 20. All right, someone else, tell me the next one. Over here.
5 times 10 raised to the 2.
Exactly. 10 to the 2 is what?
100.
Good, so we have 500. So now you sum them, 500 plus 20 plus 4. And we all know that's a quantity of 524. And this is where it gets weird when you switch to another system. When we all look at a number written down and we see 524, we instantly think that's a quantity of 524. We don't do all of this madness anymore in our heads, but you're going to have to start doing it with a whole other number system. We'll switch colors, which is binary. So now, what is the base? The number of symbols. What's the number? How many do we have to work with?
2.
Good. What are they?
0 and 1.
Good. Those are symbols. Again, don't think of them the same way yet as we do in decimal. Good. Now, luckily, places are the same. The formula is the same. This is place 0. This is place 1. This is place 2. And we're going to do a place 3 just because it's very common to deal with sets of 4 or 8 or 16 or 32, just so we're starting to operate in the kind of realm the computer stuff works in. So same thing. You have a bucket here into which you can place one of the available symbols. But we've only got 2 symbols to work with, 0 and 1 from right here. But if we're trying to figure out the sum, it's quantity over here, we'll call that quantity 3, plus quantity 2, plus quantity 1, plus quantity 0. And the same formula for the quantity is there. It's the symbol times the base to the position. Base raised to the position. So let's start over here and actually put in some numbers. We'll put a 1, 0, 1, 1. What's the quantity 0 going to be here? Symbol. What's the symbol? It's a 1. What's the base?
2.
Good. What's the power I raise it to?
0.
Good. All right. Ellen, what is any number raised to the 0 power?
That's going to be 1.
Good. So this equals 1 times 1. So it's 1. So here we have a quantity, and I'm going to write these in green underneath. That's the quantity is 1. All right. Let's go to the next one here. Switch back to red. Jason, how do I figure out the quantity here? What's the formula? Symbol times base raised to the position.
Okay, so I don't know.
What's the symbol we're using? The available symbols we have are 0 and 1. We put our symbols in the bucket here. Which symbol are we using?
So 0.
No, it's this one. We're looking at this one right here.
Oh, 1.
Good. Now I multiply that times, if we go back to the formula, the base, oh, that was a mistake. The base raised to the position. What's the base in binary?
2.
Good. Oh, I will get used to this. It's raised to the position. What's the position?
1.
Good. So 2 to the first power is what?
2.
Good. So this equals 1 times 2. Therefore, it equals 2. So far, we have a 1 over here. We have a 2 over here. You following?
Yeah.
Awesome. Perfect. This one's easy. 0 times anything doesn't matter. But let's just be nerds. And we'll do the actual math. Let's make this a better line. And I'll be a little more accurate. So it's the symbol, remember, symbol of 0 times, what's our base?
2.
Good. Raised to the position. What position are we in?
3.
No, we're 0, 1, 2
2.
for
Oh,
positions.
right.
So it's to the 2 squared. Well, we know 2 squared. What is that?
4.
It's 4, yeah. But it's 0 times 4, so it's 0. We all can look at that, but I want you to start thinking with the math. Finally, we're looking at this last quantity 3. Let me pull up participants. All right. Sudesh, you take this one. What's the symbol?
1.
Good. What's times base raised to the position? What's the base?
Base is 3.
The base of
Is
any number
3.
system is how many symbols do we have? How many systems do we, sorry, how many symbols do we have? How many symbols are available in binary?
2.
Good. So the base is always 2.
Right.
Now I raise it to the position. What position are we in?
3.
Good. So 2 to the 3rd. What is 2 to the 3rd power? 2 times 2 times 2?
16.
Nope. Look at it again. 2 times 2 is what?
8.
Nope. 2 times 2.
4.
Good. Now times 2 again.
8.
Exactly. I'll even write it out. 1 times 2 to the 3rd is 2 times 2 times 2. And again, none of us have had to deal with this stuff for many years. So it's fine that this isn't just like tripping off your tongue. When was the last time we did math like this? A long time ago. But these powers, raised to 0, raised to the 0, raised to the 1, raised to the 2, raised to the 3. This is key to understanding the number system. So 2 raised to the 3 is 8. So it's 1 times 8. So our amount is 8. So now in blue, I'm going to circle our amounts. Again, we had a 1 here, we had a 2 here, we had a 0 here, we had an 8 here. So what's our sum? 8 plus 0 plus 2 plus 1 equals what?
11.
11.
Good. Now, I want to clarify. This 11, written like this is a quantity. The quantity, we are describing it, and this is where it gets really weird. We are writing down what we all think of quantities in, which is decimal symbols. The actual, to be a real nerd about it, a better way to describe this answer would be that the answer is 11, to actually spell it out. Now, you're not going to do that in any kind of exercise I've ever seen. You're not going to. The reason I'm being a nerd about this and calling it out is I really want to specify that we're trying to determine quantities. And even in determining quantities, we can't get away from all the symbols we're used to using. We all would write down 11. I would write down 11. But when I'm looking at it in my mind, I know that what I really mean is the quantity 11. Because what is 1, 1 in binary? Let's look at the places. That's 1 times the base raised to the 0 and 1 times the base raised to the 1. So it's 1 times 1, and it's 1 times 2. So it's 2 plus 1, it's 3. 1, 1 is a quantity of 3. So you got to be super careful with what you're looking at. Up here, I've got this 1, 1. that I arrived at by adding 8 plus 0 plus 2 plus 1. And I again know that when I write down 11, I mean the quantity of 11. But it's real easy till you get familiar with this to step away for a minute and come back and go 1, 1. Oh, dang. Oh, binary. Oh, that's right. And you confuse yourself. Going back and forth. Now, there's something we do in math to remind us what number system we're dealing with. And that is when we write down some symbols, down below it, we write down which number system it's in. We write down the base. So here, this is 8 in decimal. It's a quantity of 8. This is 0 in decimal. This is 2 in decimal. This is 1 in decimal. So the answer is in decimal, and we know we're talking about a quantity of 11 things. But up here, when we were doing our math, this 1, 0, 1, 1 is in base 2. And that's where you'd write it. You write 1, 0, 1, 1, and they call it a subscript. You'd write what the base is. This tells us, hey, what number system does this belong to? Don't ever guess. Be certain. All right. So a lot going on here. And again, I don't ever want us to go past, any of us, something that isn't fully understood. Are there any questions so far? It's totally okay if there are.
I don't have any specific questions, but I would like to see another one or two.
Good. That's exactly what we're going to do next. Anyone else, any specific questions? Let's do one more. Oh, I can move that over here. Okay. Oh, sorry. I'm just getting used to Zoom controls. All right. So let's try 1, 1, 1, 1. And I'm going to be nice and write down base 2. In other words, binary. And the question is, what quantity does this represent? Now, some of you may be able to do it in your head, and that's fine. Don't shout out the answer. Let's do it one tiny step at a time, like we've been doing. And we'll write it out with our places. This is place 0, place 1, place 2, and place 3. Our base is equal to 2 because we're in binary. We have 2 symbols available. And the formula, what's the formula for quantity for each of these?
Symbol times base raised to position.
Good. Quantity equals symbol times base raised to position. Good. So in this case, we have a 1 here, a 1, a 1, and a 1. So let's start doing the math. Sudesh, you do this first one. What does this translate to in terms of quantity? Quantity equals what?
1 times 2 to the power of 0.
Good. So what does that come out to? What is 2 raised to the 0 power?
0.
Actually, it's just, it's no problem that you got that wrong at all. Math is weird. Anything to the 0 power always equals 1. Now, I can't tell you what the proof is for that. I learned it once in Naval Nuclear Power School and promptly forgot about it because I don't care. I just accepted it as true. If some math nerd figured out the proof for that, more power to them. Anything raised to the 0 power ends up being 1. Good? Yeah. Okay. I don't know why. That's one of the little things you have to take this on faith. So 2 to the 0 is 1. So 1 times 1 is what?
1.
Good. Okay. So we have a quantity of 1. I'm going to circle that in blue. Let's go back to green. All right, Susanna, do the next one. Susanna, you there? Oh, wow. I need coffee. Alexandra, hi. I do know your name. Can you do the next one?
So it's 1 times 2 to the first power,
Good,
and then that would be 2 total.
good. Oh. Excellent. So there's our second quantity. And we write again, to be explicit, the quantity is equal to 2. Okay. By the way, I should have said this earlier. You can call this the ones place, and this is the twos place, and this is the fours place, and this is the eights place. We're learning the math underneath it, but in common parlance, common speaking terms, we just call place 0 is the ones place. Place 1 is the twos place. Place 2 is the fours place. Place 3 is the eights place. Okay, but you're all doing the math perfectly well. Okay, good. Let's see. Jonas, go ahead and do the next one.
Okay, the symbol is 1.
Good.
And the base is 2.
Good.
And the position is 2.
Good.
And the total quantity would be 1 times 4, which
Good.
is 4.
Excellent. All right, Sudesh. Oh, you already did the first one. What we got here? Ellen.
So the position is 3.
Good. We start with the symbol though. The formula
The
is
symbol, yeah, sorry. So that would be 1 times, I'm struggling to say math in English.
Oh yeah. Take your time.
So
The base.
the base is 2, and then the thingy up is going to be 3.
Exactly. And we call that the power or the exponent. These are math terms that there's explicit exact definitions for. I haven't cleared them up and I should, but yeah, to the third. So equals 1 times, and what is 2 to the third
8.
again? Excellent. 8. All right. So let's circle that in blue. So now we can go the sum of 1, 1, 1, 1 in base 2 is equal to 8 plus 4 plus 2 plus 1. What does that equal?
50.
Good. So let's start to explore a couple of things. If you have a collection, actually, go back. I'm going to write this in English. 1 binary digit has a name. What's it called? Anybody know? It's a bit. It literally stands for, and we've heard it all before, binary digit, a bit. 8 bits, 8 binary digits. That'd be 1, 2, 3, 4, 5, 6, 7, 8. You might have 1, 1, 0, 1, 0, 1, 1, 0, for example. 8 bits. What's that called?
Byte.
A special
Byte.
name. A byte. Excellent. And there's a whole reason why 8 bits is really popular and common inside computing. Another one is 16 bits and 32 and 64 and 128. You can kind of see a pattern here. Okay. All right. Let's get a little more advanced. I think. Oh, I did too many. That's 8 of them. we have place 0, 1, 2, 3, 4, 5, 6, and 7. Now, I want to ask if anybody can figure out, one, the minimum quantity we can represent. That's a trick question. It's always 0. What's the maximum quantity we can represent with 8 binary digits?
Isn't like
64?
255?
It's 255, and let's prove it out. Let's say we had ones all the way across the board. That would be the highest quantity we can represent because we only have the 2 symbols available, 0 and 1. There's nothing we can do to make this quantity be any higher. And we know that this is our 1's place. This is our 2's place. This is our 4's place. 8's. What's the next one?
16,
16's place.
32,
And then 64.
64.
And 128. So we could just add those up. And you will get 255. Now, one thing that can trip you up, if you have 8 bits, 8 binary digits, the question is, how many unique amounts can we represent?
$256.
Good. It's not 255. Why?
0.
Because 0 is an amount. Good. Awesome. Okay. Now, I'm going to be giving you homework on working with binary. Okay. Some of it's just going to be simply taking like 4-digit numbers in binary and figuring out, I'm going to put a 2 here and finding out what is it in decimal, or taking some number in decimal and making it equal, what is that in binary? Back and forth, okay? Converting from binary to decimal and vice versa. So, any questions on this so far? It's totally okay if you want to do another one. I have no problem with it at all.
I don't have a question, and
Yeah.
this might be on my end,
Go
but
ahead.
I don't know if it's static coming through on your end or if it's just my audio.
I kept hearing a little bit of crackle too. Is anybody else noticing crackle?
Yes, a tiny bit.
Okay.
Yes.
It's
Is
not
it-
terrible, like it's
is it
not
when I
taking away
talk?
from what you're saying, but it seems to be, yeah.
It's when I speak, right?
It seems that way.
Okay. Dang. I had high hopes for this setup. All right. It's an experiment. Okay, good. Then I'll do some experiments after class when it's just me in the Zoom meeting, and I'll actually talk to myself and see what I hear and see if maybe there's a connector or something that's a little off, okay? That makes it all the more important if you can't hear something I say because of the scramble, interrupt me immediately and go, I didn't quite catch that, okay? All right, does anybody want to see another one of just going from binary to decimal? Oh, I'm hearing it too. Little buzz. All right, so let's see if we can kind of think backwards with this. Let's say you had a number like 75 in decimal. How would you figure that out in base 2? Any thoughts?
I don't remember. Do you
I don't
divide?
care. And by the way, for people who've done the training before, there might be a formal way to do it. Can anybody just think with like, how would I do that? Even if it's ugly and it takes a long time, I don't care.
I would just fill the place until I reach the number, and then I would adjust with the tiniest one.
God, that is brilliant. Yeah, you're totally right. Like I would go like this. Well, I know this is the ones place, and this is the 2, and this is the 4, and this is the 8, and this is 16, and this is 32. Well, first I go, what's the maximum I can do with these 5 things? I've got 32 and 16, that's 48, plus 8 is 56, 60, 62. So the maximum I get is 63. That's not going to get me there. All right, then I guess I need the 64. All right. Well, I know I need at least a 64. So now I've got my 75. I take away the 64. What have I got left there?
11.
Good. All right. Well, a 32 is way more. A 16 is way more. Oh, I can use an 8. Take the 8 away. I've got 3. Well, I'm not going to need a 4 because that gets me over. The 2 will get me close. So let me put 1 there. So I'll pick up here. 3 minus 2 is 1. Well, I have a 1. That's how you can do it. Now, there's other formulas that you can use, but I kind of like that because what it does is it reinforces, Ellen, you kind of thought with it the exact right way. It's like, well, it's the place values that matter. What's the maximum quantity? What combination of these places is going to end up with what I need? So you'll be doing some conversions like that. And I'm not doing that particular like conversions in the homework because you're going to do a ton of that as an engineer. You're not. Okay. I'm doing it just to reinforce exactly what Ellen kind of brought up, which is learning to think with the relative place values here, the 1s, the 2s, the 4, 8, 16, 32, and 64. I want you to become familiar with that progression. That's all. So you'll do some back and forth between binary and decimal. All right, how are we doing? Anybody want to see another example? Any questions so far before we add some complexity?
I think I'm good on this part. But
Good. Yeah, and again, if you get to the homework and you're like, wow, that completely didn't do well, you can go back and watch again, or you can just say, hey, Eric, can we jump on a Zoom real quick? And we'll pop into it, okay? That's why I kept this class size small, is I want to be able to help each of you as we need. Okay, so I want to just briefly talk about this weirdness called hexadecimal. Hexa and decimal. Decimal meaning 10 and hex meaning 6. That tells you what's the base for this number system. How many symbols do we use?
16.
We use 16 symbols. What are they? Anybody know?
0 up to 9.
All right. Now, what do we do when we get here?
We represent 10 by the letter A, and we go on up to F, which represents 15.
9, 10, 11, 12, 13, 14, 15. So, okay, the 9 is our 10th symbol. Yeah, okay, good. We got that right. So here's a quick question. Who has already learned or worked with this hexadecimal number system before in this class?
Yeah, I did some
Okay.
class exercises in this base systems, including hexadecimal.
Good. Anyone else?
Yeah, I have before.
Okay.
Nothing in depth or anything. I just always knew what it was and why it was that way.
Okay. I just want to show you that nothing, even though it's weird because we're using letters, nothing about the math behind the system changed. It's just now super important to recognize that we're dealing with, let's see, we're dealing with symbols. So you have places. Let's use 3 of them. We have place 0, place 1, and place 2. We, of course, have buckets into which we can put one of the available systems or symbols. The formula for a quantity is still exactly the same. It's the symbol times the base raised to the position. Nothing about it changes. You just need to know that the symbol, these quantities are weird. That's all. We know the quantities for these because we've seen these symbols our whole lives. It's these new ones we have to get used to. So let's take a weirdness of 2C3. And let's look at the equations. Let's figure out this first one, second and third. The quantity here is equal to the symbol. What's the symbol?
3.
It's a 3 times, what's our base?
16.
Yeah, 16 symbols available, raised to the power of make that come back. Come here, what happened? All right. It's coming back. Okay. So 16 raised to the 0 power. Now, anything raised to the 0 power is what?
1.
Good. So now we have a quantity. All right. Sudesh, I want you to take this one. Quantity equals symbol. What's our symbol?
C.
Good. And what's our base?
16.
Good. Raised
To
to
the
what
power
position? Good. Now let's put in a quantity for C. What quantity does it represent?
12.
I'm writing it up here, 12, exactly. So it's 12 times, now what's 16 to the 1?
16.
16, exactly. Anything to the 1 place is itself, is whatever number it is. So I can't do, well, I can do this in my head. Anybody know what 12 times 16 is?
192.
192.
192? Good. We now have another quantity. All right. Alexandra, can you do this last one?
So that would be, start with the symbol, so 2,
Mm-hmm.
and then times 16 raised to the 2nd.
Good. I don't know what 16 raised to the 2nd is. I believe it's 256.
Yeah.
So what is that? 512. Okay. So if we add those together, we have 512 plus 192 plus 3. That's 6 and 3. 4 and 3 is 7. And 1 and 9 is 10. It's a quantity of 707. So 2C3, that was a mistake. I just erased some stuff. 2C3 looks really, really weird. It's not intuitive unless you spend a lot of time working in hexadecimal. But I just wanted to show you that all of the rules are the same. Nothing about it changes. This is not one that you're going to have to spend a lot of time doing a bunch of math in or diving into, but there is a pretty common area in web development where we do use hexadecimal. Does anybody know what that is?
Colors.
Say it again.
Colors.
Exactly. Ellen's spot on. There's this whole concept of what are called color codes. You can subdivide all of the available colors in the world. This is a ton of colors. And any individual color can be described with a series of hexadecimal numbers.
I have a question.
Yeah, absolutely.
Not necessarily on hexadecimals, but do we in real life need to calculate what is it in a decimal system? I mean, is there a purpose behind that, or is
it's
just
pretty rare? Part of the reason that I do teach this is, one, there are some programming constructs you can use where you actually will set up a like 4 or 8-bit construct in your program, and you'll use some combination of binary digits to represent factors in your program that you want to keep track of. It's called a bitwise operator. We're not going to get into all the details of how it works until much later, but it's a really powerful way to keep track of objects that can have multiple combinations of factors applied to them. We'll just leave it at that. And when you're doing those, if you don't know your basic binary, you get destroyed in trying to debug it. And they're actually relatively common. So the answer is hardly ever. But when you do, I want you to be able to fall back on the fundamentals of what's the place, and the fact that a quantity is always equal to the symbol times the base raised to the position. I want you to understand those things as the number systems that are used in the Western world. So if you ever get one of these, you can go, oh, I can do the math on that. I can go 1, 1, 0, 0, and I know that's equal to 12. And you'll see that, you'll see 12 inside a computer program, and you go, oh, 12. Let me reverse that, and it's 1, 1, 0, 0. That means I'm keeping track of 4 possible factors you could apply. This one's a positive, that one's a positive, this one's a negative, and that one's a negative. You'll map all this out. Again, it's kind of nerdy. It's this whole concept called bitwise operators that you'll get to much later, but it's a direct application of binary, and you need to go back and forth. Does that give you at least a little bit of like reason why you'd want to know it? Ellen?
Yeah, thank you. Sorry,
Awesome.
I didn't unmute.
Perfect. And that's a great question. In fact, what I really like about that question is this. I'm trying to keep this class to contain data that will affect your ability to apply yourself. You're being an engineer. I wonder what it is that's causing that feedback. That is really irritating. All right. I may have to get a different setup. I apologize, folks. Okay, that's a lot of stuff. Yeah, it's happening again. Let's look here at our agenda and make sure that we're not losing track of anything. Bits, bytes. Okay, here's what we're going to do. There's a whole section I have that I want to do on binary math. I'm going to move that out. We're not going to dive into that right now. We'll come back to binary math. It'll give us an opportunity to review any homework you do on converting from binary to decimal and vice versa. So you will have homework there, but we're not going to do the math parts of this right now. We'll come back to that. All right. because I want to switch gears a little bit, get out of math land, and start talking about how CPUs work and everything. All right, it's 9:15 my time. We have about half an hour left. And I want to talk about a key aspect of computers. So I'm going to go back here. And we're going to go in here and we're going to talk about storage and memory in a computer. So 70 or 80 years ago, when computers were in their infancy, there really wasn't a way to store information in a computer when you turned it off. They didn't really have that ability. As computers became more powerful and actually started to do useful work, it was quickly recognized that we needed to be able to have a place that the central processing unit, it may not have been called that in the early days, but the part that was in control and was doing all the work, it needed to be able to take data and put it into locations that the CPU could move data in and out of. And these were, of course, physical devices. Now, there's a lot of different types of these that have happened over the years. Am I not sharing anymore? What happened? Can you not see my iPad?
No.
Okay, hold on just a moment. I don't know what changed. Okay. So we knew that the CPU needed to be able to have places that it could put data into and out of. And of course, we're talking about the real world. It's a physical device. You need to be able to put data in. But let's talk about this data. Whether it represented text or whether it represented numbers or anything else, there's only one form we could store that data in. What is that form?
A bit.
Say it again.
A bit.
A bit. You're spot on. A 0 or a 1. Some pattern of zeros and ones. Now we're going to get into stuff later on about, well, how would I represent text as a pattern of zeros and ones? We already know how to represent numbers. We just went through that. We'll get into text later. But the point is, Ellen's totally right. This data here is just a series of ones and zeros. So we're going to talk about a few of the different devices over the years that we used to store this information. But the thing to realize about any of them is that all the device needs is make a 1 or a 0 permanent. That's all. Now, permanent means two things. The first is it stays there while the computer has power. 2, stays with no power. Those are two different things we'll explore. But when it comes to the device, all we needed was a way to make a 1 or a 0 permanent. The first things they used will blow your mind. It was literally a physical device, probably about that big. Say, this is my iPad, about maybe 2 inches by about, say, 9 inches. And it had a physical handle at one end that you could hold on, and you could swing it over and it would make contact with the other side. It was literally a switch. You can think of it as a breaker. How many of you have ever turned off or on a breaker in an electrical box? You move it from one position to another, and that means electricity, that's my electrical spark, can travel through it. So they would literally have in a machine hundreds and hundreds and hundreds of these switches. And if they wanted to store information, like a 1 0 1 1 0 0 0, etc., they would literally either close. Let me do that with a blue is open or is closed. They'd close the switch, or we'll do it in red. They would open the switch, all with no power. And then when they turn on power, well, electricity can go through that one, but not that one. You can go through that one and through that one, but not that one and that one, and so forth. And now your electricity gives you your 1 0 1 1 1, etc. That's how they actually had to do it. They had to literally go into a big room and modify all these physical switches that were massive. But the concept's still the same. We managed to store the answer to, is it a 1 or a 0 in a physical device? Any questions so far? Okay, moving forward a little bit. We're not going to do a big giant history lesson here, but some really, really amazing nerds found a way to take little teeny magnetic donuts. They're tiny little rings, and they could run a wire through it. Let me do that in a different color. They could run a wire through it. See how it goes in, then comes out the other side. They could run a wire through it, and they could take another little teeny bit of electricity in a little teeny wire that goes right next to it. And if they put electricity on that, the actual magnet itself would change physical characteristics, and it would stop electricity from going through. So we use one little bit of electricity to control the state of a magnet. This is where we set the data by deciding whether or not we're going to put electricity next to the magnet. And now, whenever we turn on electricity, it either will or won't go through the wire because of the magnet. Pretty nerdy, huh? And super hard to make, and super hard and super expensive. But it took us from this size of a big giant switch down to something that was, well, you could fit about 20 of them on your fingernail. So in a space that big, you'd have 20 by 20, you'd have about 400 of them. Pretty amazing. We're getting better. And we're capable of storing our 1s and 0s. But you still have to have power on. And as soon as you turn the power off, it all scrambles and you have no 1s and 0s anymore. We needed something that was permanent. And now I'm going to introduce 2 terms: volatile and non-volatile. And there is a reason we're getting into this. Can someone explain the difference between these 2 terms when it comes to memory? A device to store data. Anybody have an idea?
With volatile, it's when it is like it loses the data, like it doesn't stay.
Lose data when lose power. which tells you non-volatile, keep data when lose power. Now I say lose, it sounds like it's a bad thing, like someone pulled the plug out of the wall. It also just means turning off the machine. So these two terms, volatile, non-volatile, volatile means like capable of change or has a tendency to change. If you describe someone as volatile, their emotions can go up and down. Here, we're not talking about an emotional state. We're just talking about a physical device. And Alexander's spot on with volatile. If you lose the power, you lose the data. How did we crack the non-volatile? How do we make a device that was really small? We didn't have to operate on these big giant mechanical breakers or switches, but that didn't need power to do its job. Does anybody know some of the devices we've used over time to do that? Magnetic tape was one of the big breakthroughs. And there's a very specific reason we need to understand how magnetic tape worked for non-volatile storage. How many of you have ever in your life used a cassette tape to listen to music?
I definitely have.
Okay,
I
good.
did.
Yeah, okay, I don't feel that old. All right, look at the time. All right, this is the last thing we're going to cover. So tomorrow. Okay, so this is kind of interesting. First, if you have a ribbon of tape, that's what's inside there. It's important to recognize that the whole surface of it is coated with a magnetic material. The other important thing to know is that, let's take this ribbon of tape, erase it. Oh, that was a mistake. Here we go. Let's use a different color for this. You can have a little teeny device that would go right up next to it, called a head. And the head did two things. One, it could write data. Two, it could read data. Let's look at write. Let's say, this tape can move back and forth, and we've moved it. So there's this one spot right here on the tape where we want to store a 1 or a 0. This head can carry electricity. So I'm actually going to use a battery to start symbolizing electricity. And if you send electricity to the head, the exact spot can change. So suddenly it stores either a 1 or a 0. So we store a 1 or a 0. Now, to get really nerdy, what it means is this magnetic material over here, it's made up of tiny little particles. We can get all the particles pointing in one direction or pointing 90 degrees from that. It's one of the cool things about magnets. They either can point in one direction or another, and it will be perfectly aligned. Magnets are awesome. So you can use electricity to do this madness. Now, I don't know who figured this out. There's some kind of next level genius, but just take it for granted that they could actually take electricity and use this physical device. And when it got close to the head and they went boom, shoving the electricity, it would align all these little particles, and all the particles would all point one direction or another. And now you have, and they would stay that way until acted upon by an outside force, until the head came along and put electricity through, or if you put a big magnet next to them, which is a horrible mistake. But you would have either a 1 or a 0 permanently stored. Any questions so far? All right. So now we have this concept of a cassette that has, I'm going to do this in a different color, this magnetic tape round around it. And then these are called spools. The round spinny thing is called a spool. And we've all seen it. It can go back and forth, right? Little gears kind of turn it one way or the other. And so we can now put a little head in here. Let's put a boom. Put a little head right there, okay? There's your head. And now the motors can move us back and forth to the exact spot where we either want to read some information or write some information. That's how we accomplished permanent, or what's the word? Non-volatile data storage. And all you do is you'd have electricity coming into the head that was either on 5 volts probably, or off 0 volts. And it would come in this pattern: on, off, on, off, on, like this. It would come in a stream, and now you're laying down 1, 0, 1, 1, 1, 0, 0, 1 onto the tape. And it's there permanently. We accomplished magic. We have permanent storage of a tremendous amount of data in a tiny little space. Questions? Okay. The last thing we're going to cover today is this interesting term called RAM. Can anyone tell me what it stands for?
Random access memory.
Can anyone explain what it is?
It's the working memory of the computer, where data is temporarily stored.
It's volatile.
Good. Big picture, inside a computer, we already know we have a power supply. We already talked about that. And then we have this big giant thing called the motherboard. And on it is our CPU. Well, we have other data storage that we'll call a drive. We all have used drives. This is non-volatile. Getting data back and forth. Let me do that in a different color. Getting data back and forth from here takes a long time. It's slow. Why? Because the drives have to spin around with motors and it takes a long time. We'll get into that part later. We need a place right next to the CPU where we can put data that's fast. We need working memory for the CPU, temporary data storage, volatile, excellent. That's what RAM is. Why is it called random access memory? The first memory we had to use for this was actually these tape drives. Now, we've already said these are non-volatile. That's permanent. So it may not have been the best option, but it was about the only option for the CPU to get data from. It was that way for many years. So let's talk about one specific drawback to these, because they were a big improvement in computing when they came out. Let's say you have the tape coiled around here and over to here, but pretend we stretched it out all the way from the start of it to the end of it. It'd be quite long. And all along here, we have data. We might have a chunk of data for one program, a chunk of data for another, and another. We've got little sections on here where we have data. Now, this is where it gets ugly. The CPU needs data. Data, question mark? It knows that it's on this tape drive somewhere. And it even knows where. You could call this, area 1 and area 2 and area 3 and so on. It knows it needs data in area 5. So it tells the motors to spin and make it so that the head and the tape coincide to area 5, and it reads the data. Any questions about that? Good. Here's where the term random comes in. It means, quote unquote, if the CPU asks for an available piece of data at random, how long until it arrives? Let's just think about this for a minute. Your program needs a piece of data. Pick one at random. Can we know how long it will take for the computer to get that data?
We need more information, like how long is the tape and what's the frequency that that thing
Speed
is
and all that.
turn.
Here's what ends up happening. Because of the fact that when a computer asks for data, we don't know, we can't, or I'll say this, we have to think with the worst case scenario. And the worst case is that the head happens to be pointing right here at the start, and the data we need is right here at the end. And what I mean by wait is the computer is literally sitting there. It cannot move forward. It can't complete its instruction until it receives the data. And so in building the computer, we had to build it such that when we ask for data, we wait until the worst possible situation of time has elapsed. Even if we happen to get lucky and the data we need is right here instead of at the end, and we get it instantly, you have to build the machine to account for the worst possible time lag. And so this tape situation was a real big improvement. But it had that tremendous drawback that we had to account for the worst case. So the solution they come up with was, well, make the motors that turn this extremely fast. But then you ran the risk of breaking the tape if it stopped too quickly. And there's some other concerns. So some geniuses came up with no moving parts memory. No moving parts. This is what RAM is. What it means is we're gonna have a bunch of individual little chips, little teeny electronic components, and we can ask, think of it as a grid. We can ask for any single grid with its X and Y axis, essentially. And if we ask for one at random, it's the exact time. It's equal time to pick any one of these. It doesn't take any longer or shorter to get any piece of data out of it than it takes for any other piece of data. I think you can see the advantage immediately. It's a massive ability for the CPU to go faster. So random access memory means if you pick a piece of data at random, it takes the same amount of time to retrieve it as any other piece of data in the device. Not true here in tapes. They are not random access. These devices, these chips, they are random access. So when you go out and buy quote unquote RAM, now you know what you're actually buying. You're buying an electronic device made up of chips. And the chief advantage is when you want any piece of data out of it, it's as fast as it possibly is, no matter what piece of data you want out of it. Any questions? Okay, good. That's enough. We went over a little bit, which I appreciate. Okay. Tomorrow we're going to dive into how the CPU works. And we needed this information about RAM and specifically up here, the CPU needing access to, how did he describe it? Working, was that you, Jason, that said that? Working memory for the CPU, temporary data storage, right? Jason, was that, I think you were talking about that.
Yeah, I believe so.
We're going to get into like how the CPU, how the CPU uses that and how it works. And when we get into it, that's where we're going to learn information that'll help you in debugging your programs later on when we're actually writing code. Okay, a lot of information. How are we all doing? Anybody got any questions?
I'm doing pretty good.
Anybody else have any like, oh my God, information overload? Everybody okay? Okay, cool. All right. So the homework I have for you tonight is actually super simple. Let me go ahead and stop sharing. And I found one of these earlier. Give me just a second. Did the fuzziness go away over the last 15 minutes or so?
Yes.
Okay.
Yeah, it hasn't been too bad since you last acknowledged it.
Okay, I think that the USB connector wasn't steadily plugged in. We'll see though. All right, I'm going to show you this little page. This has been around for a very long time, but it's super simple and it solves a very simple problem and I love it. Everybody click on that link, and then I'm going to share my screen and show you how to use it. All right. Watch me at the top of the screen, click refresh, and check out these values here when I do. Every time you refresh this, you get a new set of problems. And it's really simple. This is decimal, converted to binary. This is binary, converted to decimal. That's all it is. You can also, I think, click new quiz, and it does the same thing. What I want you to do is a minimum of 8 of these. If you want to do more after that, just to get comfortable with it, that's fine. But please do at least 8 just to work through this thing. And if you need to go back and review, do so. If you need to look up some resources online on it, do so. If you need me to pop on a Zoom call with you or a phone call, let me know. Okay, good. Oh, Ellen, I totally missed that earlier. I apologize. All right, that's the homework for tonight, is just do these conversions back and forth. There'll be a lot more for the week that I'll assign you tomorrow, but we've only got until tomorrow until we have class. Woo, that was a whole lot of stuff. Thank you for going through that. I especially appreciate the involvement as we're doing the binary stuff and asking questions and making sure you understood it. Anybody got anything that they want to cover before we leave? Okay. Sudesh, Jonas, start your day. The rest of us, end your day and relax. I will see you all tomorrow. We'll dive into the CPU. Just so you can look forward, it's not going to be very long till we're actually going to start writing code and put some of this stuff to practical use. I just want to make sure the fundamentals are laid down. And if there's any feedback you guys have, anything you want me that you would like addressed or changed, or just some advice, PM me inside of Discord. I want to hear anything you have to say. Other than that, have a great night. Appreciate it. And I will see you all tomorrow, same time.
Thank you. Good night.
Good night.
Yeah. Bye.
Okay, thank you.